So we often use color in data visualization, and it's important to understand how best to use color to trigger perceptual cues and other ways of sensing the data. These rules have come from Colin Ware's book on information visualization. As we're picking out colors, it's often better to think of colors not in their component values that are used to store them in the computer, basically red, green, and blue, or a certain portion of red, green, and blue. It's better to think of them in a more natural set of three components, basically hue, saturation, and value. Hue is basically where the color is in the color wheel. Is it red, yellow, green, cyan, blue, or magenta, or someplace in between? Saturation is how intense a color is, what is its distance from a dull gray to a vibrant version of that hue. And then value is how bright the color is, its distance from black. And so if you're given a color in RGB, there's a little bit of code here that would show you what the color should be in HSV. And a similar color space is used anytime you're picking colors in applications. For example, in Microsoft applications, you get this color space where hue is shown horizontally as we go from red to yellow to green to cyan to blue to magenta and back to red. And then saturation is vertically, and we're moving from a gray through some muted versions of the hues all the way to the full intensity versions of the hues here. And so you're picking your hue and your saturation here in this space, and then value is kind of denoted here, going from black to full intensity. And in this case it's going to white. This isn't quite a value axis, but it's very closely related. So hues, as we've seen before, hues are a good choice for representing nominal variables, for representing categories. And we've seen that 5 or 10 hues are quite effective in visualizations. You don't want to have too many colors, but 5 to 10 different hues can be quite effective at mapping different values of a nominal variable. There's as many as 12 colors, 12 good colors that you can pick from that are based on Ward's extension of some work by Berlin and Kay. And so there's the main 6 colors: white, black, red, yellow, green, and blue. And these are uniformly chosen across cultures as being good different colors, basic colors. To that you can add 6 more colors: gray, pink, orange, brown, purple, and cyan. And so this is a good choice, starting with the first 6 and then picking colors from the next 6 if you need good colors to map to nominal variable. Saturation is helpful when you're mapping various elements of a visualization. You want to use fully saturated colors for small things in a visualization. If you have a thin line, you want to use a fully saturated color. It's easier to see this saturated red-orange and a saturated blue than a desaturated red-orange and a desaturated blue on these two lines. Both with a white background or a black background, it's still easier to see the saturated lines than the desaturated lines. You want to use desaturated colors for fills. So you want saturated strokes and desaturated fills. And so here's a bar graph with blue and orange. Using desaturated blue and orange, you can still see the differences. When you have saturated large fills, the aesthetic can be a bit harsh, and also it can be a little bit distracting. So it's better to have desaturated fills and saturated strokes. It's also important to pay attention to contrast. You want to use brighter colors in order to gain attention. So here, for example, I've got desaturated bars and I've got one saturated bar in case I want to draw attention to, this particular data value in a visualization. And then you want to pay attention to brightness contrast, not just color contrast. So contrast means a difference, and so ordinarily contrast deals with luminance or brightness, and you look at the brightness of one color versus the brightness of another color on that in that, or the value of one color versus the value of another color. But you also want to make sure there's good luminance contrast. Color contrast is often just a difference in hue, but not necessarily a difference in brightness. And so here I've got orange text on top of a blue hue, and I'm just changing the saturation and value of this blue hue from black to full intensity to white. And you can see that even though there's sufficient color contrast, there's differences in the color, there's not much difference in the brightness here, and it becomes very difficult to read. And so you want to make sure you maintain good brightness contrast, value contrast, in addition to just color contrast. So the recommended usage, you don't want to use colors to represent quantitative variables when you want to see the when you want to measure the difference between neighboring values in a visualization. It is a good indication. We can use density to represent brightness or value, and then we have saturation and hue. It is good for ordinal variables. So we can tell that one color is brighter than another color. We can tell that one color is different than another color, or closer to, for example, red, or by different hues. Or we can tell that one color is more intense than another color. So these are good for ordinal variables, even though we can't tell how much different they would be. And for categories, hue is an excellent choice for categories. Changing the value or the brightness, or changing the saturation, how gray a color is versus how intense, is not as good a differentiator of categories. So the horizontal axis of a bar graph, you don't necessarily want the bars to be going between grayer and brighter. But it is good to have them be different colors, different hues. You can use color maps to represent quantitative values, and this is a very common thing to do. We see it in weather maps all the time, for example, when we're displaying the temperature in a region, in a geographic region. But the choice of color maps can be problematic. And so, as we saw before in this three-dimensional visualization, we're just using an ordinary rainbow color map. It's darker here, it's a little dark here, and it's brighter here and here. And those changes in brightness in the colors chosen for the color map can interfere with the perception of light and shadow used to get the orientation of the surfaces here. And it looks like this blue area is darker than it should be by the shading, and it looks like this skull has a divot here when it actually doesn't. So it's best to avoid brightness and saturation variations in a color map for illuminated three-dimensional objects, and in general, mapping brightness and saturation to actual quantitative values is more error-prone than hue maps. So if this is a direct hue map, then it's easier for us to make a reference into a legend for what those values are. And this overcomes the problem hue would ordinarily have as a quantitative variable representation, because we have this legend here on the side. So here's some examples, 2 dimensions and 3 dimensions. We've seen the rainbow map is not a very good choice for 3-dimensional data because of its light and dark values. But in 2 dimensions, it does a pretty good job of showing positive and negative values in this region. A light to dark map is good for showing magnitude, not necessarily positive or negative here, but just magnitude here. And it's really a poor choice. You don't want to use luminance mapping to map variables that are plotted on a 3-dimensional surface, because it really interferes with the lighting. So for a 3-dimensional surface, you want to try to pick some hue scale that doesn't affect saturation or value of the color, so that the shading isn't affected by the mapping of the variable that is plotted over the surface. And so in these two cases, we have uniform brightness, uniform value, and saturation, well, at least uniform value across the color map. And so it doesn't interfere with the lighting of a three-dimensional shape, although these aren't necessarily the best color maps to use for 2 dimensions, where you can get away with more of a change in luminance. And there's a really good website for choosing colors called colorbrewer2.org, and I'd encourage all of you to take a look at that website. It's designed for picking color maps for geographical data, and I'll point you to it here and encourage you to go take a look at it right now. So we've learned that it's best to think of color for data visualization as being a hue, a saturation, and a value. And we don't always want to choose a rainbow color map when we're displaying our data. We want to look at what kind of data we're displaying and choose the best color map for that data.
Good.